It's a pleasure to introduce David Wajc. He's been a grad student at CMU for a couple of years. When I first met him, he was very interested in puzzles, and we had a lot of interesting conversations about that stuff. Later, he's gone on to do real serious research, and he's going to tell us about great work on matching.
Thanks, Lenny. Thanks, everyone, for coming and suffering through this pizza. So today I'm going to tell you about joint work I did last fall while visiting Ola Svensson at EPFL. It's joint work with Budima Gamma, Michael Kapralov, Andreas Majori, and Ola Svensson, titled Online Matching with General Writers. As usual, in a regular preface, any questions, please interrupt me with anything that will help understand what's going on. A discussion is more fun than a monologue. Okay, so let's start with the following motivating application. Let's say you have a number of buyers, in this case my co-authors on this paper, and sellers who show up in an online fashion, each of which is interested in selling a perishable item. Okay? So first seller shows up, is interested in selling a strawberry, and everyone wants to buy a strawberry except for Andreas, who doesn't care for them. So maybe we'll sell the strawberry to Michael. Another seller shows up, is interested in selling an apple, who doesn't like apples. So maybe we'll sell this apple to Ola. Now another seller shows up, is interested in selling a blueberry, but unfortunately only Ola cares for blueberries, and he's already eaten his fill, so that blueberry is going to be wasted. Another seller shows up, is interested in selling a mango, but only Ola and Michael are interested in mangoes, and they've both already eaten their fill. So this piece of fruit will also perish and be thrown. Okay, a little more abstractly and a little less tongue-in-cheek, what's the problem in this slide? This is precisely the online bipartite matching problem. We'll have run this thing on the left. The underlying input is a bipartite graph, initially unknown. So the only thing we know at the beginning is the nodes on the right-hand side, which we'll refer to as offline nodes. And nodes on the left, which we'll refer to as online nodes, show up one after another together with their edges. What an online algorithm has to do is decide immediately and irrevocably who to match this newly arrived online node. Okay, so say in this case maybe we'll match the second edge, another node shows up, we can't match it along its second edge because that node is already matched, we'll match it to someone else, and so on and so forth. Notice that the last two nodes we didn't match at all because they were already, all of their neighbors were already matched and we cannot revoke up to this match. Okay. Good, so the size of the matching we've output here is 3. The optimum is really easy to see if you just look at the horizontal edges. This is a matching of size 5. So we got 3/5 of the hindsight mode. Okay, and this will be our, if you've never seen online algorithm before, this is how we're going to measure our algorithm. What we refer to as competitive ratio, which is just the worst case overall inputs of the expected size of the matching output by the algorithm. Is this me? Is this anyone else speaking? All right. The expected matching size over the optimum matching size. Dynamics clear? Questions? Okay, just to double check, let's quickly consider the first algorithm you think of for this problem, which is the greedy algorithm. So the greedy algorithm, when a node shows up, you'll just match it to any of its available neighbors, if it has them. This will output a maximal matching, not maximal, and this is 1/2 competitive. Unfortunately, no deterministic algorithm can do better. So this is the entire class of deterministic algorithms, basically. Just be greedy somehow, get 1/2. And the following very simple example kind of illustrates this. So you have one online node showing up, has 2 neighbors. The deterministic algorithm will always match the same neighbor, say this one. And then another node shows up that only neighbors this matched neighbor. Okay, so we could have matched 2, we only matched the 1. Okay, so that's it for deterministic algorithms. So the natural question is, what can you do with randomization? Okay, any thoughts for a candidate algorithm? Just to make sure we're all on the same page. Random, right? Okay, so random doesn't work. Here's a simple example. So we'll have n over 2 nodes, I guess n nodes on either side. This is the online side. This is the offline side. Nodes will arrive in this order. Here's a perfect matching. And every node here neighbors every node here. So in addition, we'll also have like a complete bipartite clique here. Okay, it's barely an exercise to show that basically pretty much every node that shows up in the first n over 2 will match diagonally, which is incorrect. And now the second batch of n over 2 nodes will not get matched to anyone. Maybe up to like some little order of 1 term. Okay? Good, so at least like the first thing that comes to mind doesn't work, but a very beautiful algorithm called ranking, introduced by Karp, Vazirani, and Vazirani, does. And it's, so, yes, Boris.
The arrival is adversarial, the algorithms were randomized.
The arrival is adversarial. We're allowed to use randomization for our choices. Next. Good, so this algorithm is so sleek and elegant, I can describe it in exactly 2 lines, and maybe one small animation. So as our first step, we'll permute the offline side, like so. Okay, some of you missed that animation. So we'll permute the offline side, like so. Okay, good. And then what we'll do is we'll just perform exactly the same thing the greedy algorithm would do, only use this permutation as a random tie-breaking rule. In particular, when a node shows up, we'll match it to its highest neighbor according to this permutation. Okay, so first node shows up, it happens to neighbor the first node according to the permutation, we'll match it. Second node shows up, neighbors the first and second. First is taken, so we'll match it to the second, and so on and so forth. Okay, question in the back? No. Okay, so this is just an instantiation of the greedy algorithm, right, with an additional randomized tie-breaking rule. So it definitely gives you at least 1/2 of the optimum, but does it do better? Well, indeed, Karp et al. Showed that this algorithm is 1 - 1 over E competitive, so roughly 63%. Moreover, they actually showed that this is the best you can do. There is no better algorithm. Cool, thanks for your time. Okay, a little more seriously, bear with me for like a few more minutes and I'll actually tell you what the problem is that we study. Some generalization of this problem. So actually the motivating example we started with was somewhat tongue-in-cheek, right? But actually the underlying dynamics relates to a very, very lucrative business, namely internet advertising and search advertising. So for example, over the summer, my sister and her family were visiting me. So naturally, before coming, one of the things they did was look up things to do in Pittsburgh. So when they searched for this on Google, other than getting search results or 10 blue links, maybe a Wikipedia excerpt, and some nice pictures, they also got an ad for Airbnb in Pittsburgh. Okay, so here Google kind of messed up because, of course, they're going to stay with me, right? But okay, good. So what's going on kind of behind the scenes? So behind the scenes, the dynamics is as follows. At the beginning of the day, a bunch of advertisers come up to Google and tell them, look, here's our advertising budget, and these are the search queries we're interested in. If somebody searches for this query, then I'd like you to show them this ad, and I'm willing to pay this much. Okay? And this is exactly the perishable items. So when a user searches for something, it generates an ad slot. So a user searched for something, which is a keyword that Airbnb, Starbucks, and Duolingo are for some reason all interested in. Okay? So now what Google has to decide is before showing this user the search results, etc., it has to decide what ad to show. Right? Having like dynamic ads is crazy disruptive for the user experience, so you have to decide immediately and irrevocably what ad to show.
You can only show one ad?
More generally, you can do, of course, much more elaborate stuff, but let's keep it simple for this talk. Good. So maybe we'll show an ad for Starbucks, another user searches for something, maybe we'll show an ad for Duolingo, and so on and so forth. Okay? So this problem is called the AdWords problem, introduced by Mehta et al. In 2005, and they showed for this problem as well a 1 - 1 over E competitive algorithm, and that this is optimal. More generally, this motivation application of online advertising has spurred a lot of research on generalizations of online matching, maybe barring Kirk and Bala's follow-up work, which was a little before internet advertising was a thing. And in all of these extensions of online bipartite matching, we know that the greedy algorithm is 1/2 competitive, and 1 - 1 over E is the best you could hope for. And you can actually get that. Okay? Hopefully, however, I'm not going on a limb saying in a theory seminar that there are other reasons to study theory than maximizing Google's bottom line. And in addition, hopefully, you're also aware that there exist non-bipartite graphs out there. Okay, so this will be kind of what we'll study for the rest of the talk. We want to see if we can do better than the greedy algorithm, which is kind of the only algorithm we know, for more general arrivals. So what do I mean by general arrivals? Well, there are 2 models we'll study. The first is general vertex arrivals. So now maybe you have a bipartite graphs and arrivals are on both sides. Remember that in the KVV model, arrivals were only on one side of the graph, which you call the online side. So maybe we'll have interleaved arrivals, some buyers, then some items, some buyers, then some items. Or maybe the graph is just general. Right? You have a general graph and nodes show up, and when they show their edges to their previously arrived neighbors. I'll be a bit more clear about this model in a minute. An even stricter model is edge arrivals. So when an edge shows up, you have to decide immediately and irrevocably, do I take it or do I drop it? Okay, so just to make sure we're all on the same page about these two models we'll talk about for the rest of the talk. What do I mean by general vertex arrivals? We have some unknown graph, and vertices show up one after another, and when a vertex shows up, it reveals all of its edges to its previously arrived neighbors. Okay, so first node shows up, of course, no edges, no one showed up before. Second node shows up, maybe it has an edge to the first node, and now an online algorithm has to make a choice. Do I match along one of these edges to a previously arrived neighbor, or do I forego this edge forever? Okay, so maybe our algorithm here will decide to match. Another node shows up, neighbors 1 and 2, we can't match it. By the way, notice that this already shows the graph is not bipartite in this example. Another node shows up, neighbors 1, we can't do anything here either. Another node shows up, its free neighbors are 3 and 4, so we have some choice here, and maybe our algorithm decides to match to, say, 3, and so on and so forth. Dynamic clear? A few nods here and there would kind of help. Yes, thank you, Charlie. Thank you, Boris. Thank you, Gore. Okay. If you tilt your head a tiny bit, you'll see that the optimum matching here has size 4, right? And as before, being greedy will give you a maximal matching, so 1/2 competitive solution. And again, as before, since this is a more general model than the model studied by KVV, you cannot do better without the use of randomization. Okay? So the question is, can we do better than 1/2? For the bipartite one-sided vertex arrival model of KVV, we know that greedy with some randomized tie-breaking rule allows us to do that, right? The ranking algorithm we saw earlier. However, for this more general model, actually, this is no longer the case. If you want to do better than greedy, you have to explicitly not be greedy. Okay, so even if we have a possibility to match, you should sometimes say, you know what, I'm good, I'm going to keep both of these nodes around so I could possibly match them later. Okay, if this is not so clear, let me maybe just give you like a 4-node example that shows this. Nodes 1 and 2 show up, they happen to be neighbors. A greedy algorithm, doesn't matter what your tie-breaking rule is, will match this edge. Right? If it's any kind of greedy thing. And now if 2 and 1 have other neighbors, well, you find out that, hey, actually the hindsight optimum was 2, but we only got the one lousy edge. Yes, Anish?
So your competitive ratio needs to only hold at the end or at every time step?
So that's the thing. Okay, so in case you didn't hear a question, the question is, do you have to be competitive at every point in time? So the thing is, you don't know when the input stops. Right? So as far as you're concerned, the end of the time is now. The end of the input is now. Okay?
So also this graph is bipartite, so this shows even this arrival on both sides.
Yeah, even exactly. So as Venkat pointed out, even for bipartite two-sided arrivals, you have to be non-greedy if you want to beat 1/2. Fantastic. Okay, so the question is, for general graphs, can you do better than greedy? We know we need some new ideas here. Okay, just thinking of some kind of extension of ranking is not going to work. And actually, we're not the first to ask this question. If you study the paper of KVV and kind of scroll through to the end of the paper for some open questions, you'll see that they ask specifically this question. Is ranking an optimal online algorithm for general, as in the non-bipartite case? Okay, so by what we said earlier, this question basically translates to, is greedy the optimal algorithm for the non-bipartite case? Or I guess, as Venkat pointed out, even for bipartite with two-sided arrivals. Okay, good. So that's one model. Another model we study is the edge arrival model. Hopefully the model is obvious just by its name, but if not, he'll have a couple quick animations. So edges arrive one after another. So here we have an edge between 7 and 3. And now the perishable things are no longer nodes or items or what have you, but rather the edge itself, the matching opportunity. Okay, so we have a I'll get there, an opportunity to collaborate. But you know, if we don't start working on it now, then we'll never meet the deadline, so forget it. Okay?
So wait, so the
Yeah.
previous model, you...
Oh, we're going to have to go through this again. I'm sorry. Yeah. Yeah.
if you did, the greedy says you have to, one and two must be selected, but that's
Sure.
the edge.
Yeah.
between them. But now you're saying you can try to get away from greedy since it's no good.
Yeah.
You're saying, well, we're not going to select that edge. But is that an irrevocable decision?
So basically when you,
Leave that edge.
essentially you're, yeah, I was already getting, as you noticed, a little heavy on the animation, so I thought I wouldn't add something like that. But if you, so a node shows up with edges to its previously arrived neighbors, you either match along one of these edges or you just throw away all of those edges. Okay? Same goes for the, maybe I'll try and skip these animations real quick. For edge arrivals, okay, an edge shows up, you either match along it or drop it. Okay, you'll never meet a deadline if you don't start working right now. Okay, so maybe our algorithm here tosses some random coin, decides to not match along this edge. So this is the choices of the algorithm, take it or leave it. So we didn't match, maybe 2 and 3 show up, we decide to match. I think you get the gist of it, right? Okay, so as before, the optimum algorithm, the greedy algorithm is still 1/2 competitive, and we don't know anything better. Okay, kind of spoiled actually the related work section. So let me tell you a little bit about what's known about both of these problems. Okay, so again to recap, we want to know whether or not we can do better than greedy for these problems. So one thing that's known for both of these problems is that they are strictly harder than the bipartite one-sided arrival problem. Well, I'll spare you the exact numbers, but for a bipartite one-sided arrival, you could get 1 minus 1 over e, and for both of these models, there are hardness results that show that you cannot get 1 minus 1 over e. Okay, so that rules out recreating or generalizing Karpetal's beautiful algorithm to these more general arrival models, but it doesn't rule out a better than 1/2 competitive algorithm. Right? Maybe there's something else you could do. And despite this problem having been studied a lot over the years, the only positive results we have are under all kinds of relaxations and assumptions, either about the input or about what have you. So one assumption was that the input arrives in some random order, kind of speaking to Boris's question earlier. Another assumption is that the graph has some structure. Maybe it's a restricted class, maybe bounded degree graphs or trees or what have you. Maybe edges show up in batches, not just one edge at a time. There's some result for fractional matching algorithms. So now you can match an edge, it's not binary, it's not you match these two or not. You maybe match them to an extent of 0.3 and so on. We'll talk about this some more shortly. And recently, some result was given for online matching under vertex arrivals, even in general graphs, but with the following assumption, so a somewhat easier model where nodes have a deadline. So a node shows up and says, look, you either match me by this point in time or forget about me. Okay, so nodes are perishable, but the deadline of when they're going to perish is not right now. Okay? And for this model, Huang et al. Showed that actually ranking is a good algorithm and beats the competitive ratio of 1/2. Basically because in this model, when a node's deadline shows up, you might as well match it. Right? You're not gonna gain anything by saying no, forget it, and if you could match it to someone else, maybe makes sense?
So why can't all deadlines be right now?
Exactly.
Right. All deadlines.
It's more general case.
So it's a more general case than, how do you mean? Yeah. Why can't all deadlines be right now? Right. So in the case that all deadlines are right now, in some sense there is no edges. You have no edges to your neighbors that show up after you. I'm giving you some structural guarantee about the graph. Right? If I have an edge to you, but you show up in time 10 and my deadline is 7, then essentially I have no edge. Right? Basically that's the benchmark. The hindsight opt is an algorithm that knows the deadlines, and in that case it basically ignores an edge between someone whose deadline is 7 and someone whose arrival is time 10. That makes sense? So in some sense the baseline is easier. Our algorithm will, of course, spoiler. Any positive result for our model will definitely hold for this model. The opposite is, of course, not true. Okay, so I've spoiled a little bit some of the results, but let me tell you what they are nonetheless. So for edge arrivals, we showed that the work on online matching under edge arrivals with all kinds of assumptions was not just motivated by this problem being difficult, but actually by this problem being impossible. you cannot do better than 1/2. Greedy is the optimal algorithm for online matching under edge arrivals. Okay? As I spoiled the second result, our second result is on the flip side, for vertex arrivals, even in general graphs, you can obtain a 1/2 plus constant competitive online matching algorithm.
Actually, what does this notation mean? It means that there is just a constant that you cannot beat, or there is no constant.
Oh, sorry, this should be, no, this is good. You're talking about this one or the first one?
Both.
Both, okay, so
The
here,
second one
this one should be obvious, right? 1/2 plus some constant, which I will not tell you right now, or at all maybe. For edge arrivals, what I'm saying is actually, the best you can do is 1/2 plus some little order of one term. If you're curious about the little order of one term, we show that you cannot do better than 1/2 plus roughly 1 over n.
Oh, I see. So it rules out any half plus delta.
Any half plus, I mean, if delta is greater than 1 over n, no. Okay. Other questions? We good? Okay. So for the remainder of the talk, what I'm going to do is pretty much give you the entire proof of result number 1, modulo calculations. And then I'm going to give you a high-level idea of some of the ideas that go into result number 2. Okay, so let's start with edge arrivals. So again, remember, edges show up one after another, and you have to make choices immediately and irrevocably, maybe tossing some random coins. Do I take this edge, or do I drop it? Okay. So our general approach, rather than showing hardness directly for randomized algorithms, will be to show hardness for fractional algorithms. So I kind of alluded to this earlier. A fractional algorithm is an algorithm that when presented with an edge, decides on some value to assign it, which corresponds to a fractional extent to which this edge is matched. Or a little more formally, the values xe's will be a point in the fractional matching polytope, which means they obey the following constraints. They're non-negative. Doesn't really mean anything to be minus 1/2 matched to someone. And in addition, for every node v, if you sum over all its incident edges x values, this value is at most 1. Okay, so just to make sure we're on the same page, this is a relaxation of what it means to output a matching. In a matching, these xe's are either 0 if the edge is not matched, and 1 if it is. And the first constraint is exactly the matching constraint. You're allowed to be matched at most once. Right? You're allowed to have at most one edge in the match. Okay. So why are we interested in fractional algorithms? Well, we're interested in fractional algorithms because of the following rather direct observation. Any C-competitive randomized algorithm implies a C-competitive deterministic fractional algorithm. Okay, so there's a few people nodding their heads, but I just want to make sure that this is clear. Okay, so here's basically a one-line proof. Take the x values to be the marginal probabilities for edges to be matched according to the randomized algorithm A. Okay, these are non-negative. And since each node V is matched at most once in any realization of the randomness, it's matched at most once in expectation, right? So by linearity, this, the first constraint, the fractional matching constraint, is satisfied if I take these xe's to be p's. Boris seems a little troubled. Maybe you're thinking of what I was going to say next. Okay, so here's one thing to notice. This is by no means, what I'm defining here is by no means an efficient algorithm. Right? If you want to figure out what these marginal probabilities are, one way you could go about this is just keep a table of probabilities for every set of possible free neighbors at every point in time. Right? You'll have like an exponential sized lookup table, and whenever another node shows up, you figure out what the marginal probability, how the marginal probabilities will change at that point in time by just seeing what happens in every one of these realizations. Okay? So crazy inefficient algorithm, but it doesn't matter. Okay, I'm going to let this fractional algorithm be slow. I'm going to show hardness results for a fractional algorithm, so I'm giving it more strength. More strength to it. It's not going to help it. Okay, we're clear about this. The room got super quiet, and I don't feel like this was a point we should be worried about.
So it's like you imagine running the algorithm an infinite number of times,
right?
Just taking
the average. Yeah.
Somehow the weight.
That's exactly right. That's exactly what the fractional algorithm is. So one way you could think about this up to maybe some precision issues, you could exactly imagine, as Danny said, let's say I tell you the sequence length is some n. So I could just run the algorithm up to every point, some poly n many times, and get these values up to some small error probability, right? I'm letting the fractional algorithm actually know this precisely by maybe taking exponential time. Doesn't matter. Okay, Venkat.
Do you imagine some graph which the adversary has in mind? And then the edges come in random order, or can the adversary even pick the graph based on the choices you make?
Oh, the adversary better pick the arrival order adversarially, otherwise Guru and Sahil's result shows that you can do better.
Because this polytope is defined by the set of edges, so it's a fixed polytope.
Right?
So do you have a fixed oblivious graph in mind, and the arrival order is randomized, or can the adversary just look at the choices you made and say, okay, now 2 and 3 are not going to be connected?
So we're going to show hardness for deterministic fractional algorithms. The adversary doesn't need to know what you're going to do. I mean, it doesn't need to see what you did. It knows what you're going to do, right? A deterministic algorithm, after I give it edge 1, I know exactly what it's going to do. After I give it another edge, I know exactly what it's going to do, and so on and so forth. Okay, so I don't need to, I basically know based on your code exactly what you're going to do, so I'm going to give you exactly an adversarial input for that code. Does that answer your question? Okay, go on.
For every algorithm, there is a graph. That's what you're going to show, right?
Not quite. Actually, I'm going to show a graph. No. I'm going to show a graph that screws every algorithm. Spoiling it a little bit, but you'll see it in a minute. Okay. I mean, you could do something saying, like for every deterministic fractional algorithm, there's some input that messes it up. But we show an even harder result that implies what we wanted to show.
So
Go on.
would like a randomized fractional algorithm be more powerful than this?
No, right? You could just take just by smoothing, you'll get the same thing, right? So look at the expected value, at the expected xe at every point in time. The expectation of that is just a convex combination of fractional matchings, which themselves are in the fractional matching polytope. I feel like this is getting too technical, but yeah.
It is linear, so it doesn't matter.
Yeah. So exactly. So as Professor said, all these constraints are linear. So linearity of expectation just says, there's no point in using extra randomness. Again, I feel like we're getting a little sidetracked. So maybe let's take this one question offline. Okay. Good. So for the rest of the talk, or at least for the rest of this part of the talk, we're going to show hardness for any deterministic fractional algorithm.
No more questions.
Ask as many questions as you want. I know my audience. I've got some slack here. So it's, okay, good. So what we're going to do, a lot of the previous hardness results kind of relied on the algorithm not knowing the input, which is really kind of what hardness in online algorithms is. Nonetheless, okay, so we said we're going to give the algorithm some strengths. We're going to let it be a deterministic fractional algorithm rather than randomized. So it's possibly a more general class of algorithms. And moreover, we're actually going to tell it what the graph is. Okay, you should be a little suspicious here. Not only are we going to tell it what the graph is, we're also going to tell it in what order the edges are going to show up. Okay, so edge 1 shows up first, then edge 2, then edge 3. Okay, at this point you should be calling me out for clearly misleading you. So I mean, at this point, this is just an offline problem, right? We know the entire graph. Actually, the arrival order doesn't really matter. Just compute max matching, right? This is something we know how to do even in poly time. I'll give you a one competitive solution. So here's the one thing we're going to do to kind of try and screw over the deterministic fractional algorithm. We're just not going to tell it what time the input is going to stop. So this speaks back to Ainish's question earlier. You don't know when the input, you don't know the time horizon.
So
Okay.
each graph is going to be a subgraph of a fixed graph.
Exactly. It's going to be even more than that. It's not any subgraph. So I'm basically telling you, you're going to see some prefix of this graph. Either the first edge, the first two edges, the first three edges, and so on. And you have to hedge your bets against the stopping time being here, or here, or here, and so on and so forth. Okay? Good. So imagine you have a C-competitive algorithm. Well, that means that the value you get on E1 better be at least C times the optimum matching size on the subgraph induced by E1. And it also better be the same thing for the subgraph induced by the first two edges, and by the first three edges, the first four edges, so on and so forth. Okay? So putting all of this together, we can actually write this as an LP. So if you have a C-competitive fractional algorithm, what I just said right now are just linear constraints. This means there's a solution of value C to the following LP. You want to maximize alpha. Alpha is going to be our competitive ratio, subject to these x's being a fractional matching. And in addition, for every one of these prefixes p, which you know in advance, you better have accumulated enough money to alpha cover this, the opt at this point in time. Okay? Whole idea. Good, so now if I want to show that no deterministic algorithm can do better than something, I can just give you a graph, give you an arrival order, solve this LP, and I tell you, look, no algorithm can do better than 0.5 something. Okay, unfortunately our inputs grow asymptotically, so solving LPs to optimality symbolically is a bit of a drag. But fortunately there's such a thing as LP duality, so what we'll do is just give a solution of value C to the dual LP. That upper bounds the optimal value of the primal. So that means that there is no better than C competitive algorithm, right? If we get a solution of value C to the dual LP, there is no better than C competitive algorithm. In particular, there's no better than C competitive algorithm on this particular input. Pick your favorite algorithm, doesn't matter. Pick your favorite fractional algorithm, doesn't matter. Okay, so on and so forth. We're good? Okay, so the only thing I still need to show you is the actual hard instance. Okay, and our hard instance will actually be a bipartite graph. So we actually even show hardness in bipartite graphs. We'll have n nodes on the left, n nodes on the left, well, I guess I said that, n nodes on the left, n nodes on the right, u1 through un, v1 through un. And we'll reveal the edges in rounds. And in round I, we'll have a perfect matching between the first I nodes on either side. So what does this look like? In round 1, we'll have an edge between u1 and v1. In round 2, we'll have an edge between u1 and v2, and u2 and v1, and so on and so forth. Okay, so if you're trying to figure out what the regularity here is, in round I, the ith node neighbors the first node, the I minus first neighbors the second, the I minus second neighbors the third, and so on and so forth. Yeah?
I'm confused. I mean, so you said that the distribution of those three graphs is your hard instance. So now that's not the case.
So there's no distribution, right?
No, what about those prefixes, E1, E1, E2, E1? I thought you're just uniform on those three graphs, and that's hard for your deterministic algorithm.
So no, so it's not so much a question of distributions, right?
I think you and
Yeah.
Venkat are thinking a little bit differently.
Possibly.
I think David's goal is that there's a fixed graph, but I want to maintain competitiveness at every point in the arrival.
Sure. Okay.
But you are thinking I want to make sure it falls at the end. And so if you think in your way, I think then there are number of prefixes, number of graphs. You're saying one of them you will fail.
Mm-hmm.
Well, for David, that's what
Yeah, so,
means.
but if thinking my way doesn't give the lower bound?
No, I think it's the same. It's like.
So then that three thing seems to be a lower bound, right?
So basically by a Yau's lemma or something, you could get something similar and start talking about distributions. It's definitely not a uniform distribution though.
No, but if you want half plus epsilon competitive, the middle edge you have to put half plus epsilon. And
The first thing is what you mean.
The
Yeah.
two outside things you have to get half minus epsilon.
Sure.
And then for the full graph you're not...
I mean the full graph stuff keeps showing up, right?
I see.
And that's kind of the problem, right? So if you put 1 minus epsilon on the what was it? 1 minus epsilon you said on u1, u2? No, sorry, 1 half plus epsilon, right?
No, I think
so now there's not enough room for the edge u1 v3. And that kind of maybe explains a little bit of the intuition as to maybe drop this formal definition of what the input looks like. The general intuition I have here as to why this might be a hard instance, I mean the LP from the previous slide shows it, but if you wanted to get some intuition as to why you'd look at this input, well, each edge appears in precisely one prefix as opt. And intuitively you kind of have to assign some values, some value to the edges of opt. And well, there's just too many edges to put some value on, and yeah. This is crazy hand wavy. Unfortunately, I don't have a different proof other than this machine verifiable LP-based proof. I'd be happy to see some other nice proof, even maybe longer than the 2-page proof that we have for this result. Einish.
So if I told you that you stop either time I or
Yeah.
time I times 100.
Sorry, again?
You just promise that.
Oh, if you promise that it's between time I and I times 100?
Either at time I stop at time I or I stop at time 100 times I. Then does this instance break?
Yeah, well then, okay, so the question is if you stop at round I or if you stop at round 100i, and that's a guarantee, well that's actually somewhat easy. Yeah. Forget about the useless edges. Basically, so let's say okay, you're talking about say round 1 or round 3, right? So assign some value to this edge, ignore the edges in this round, and assign some value to these edges if you get here later. Right? So in some sense, it's basically just a 2-round hardness, which should give you 1/2 plus a constant. Okay. Other questions about this input?
So if you knew that
Yeah.
it wasn't going to stop before a certain round, you could do a lot better.
Yeah, if I know, I guess actually it's
If it
even,
wasn't going to stop in round 2.
yeah, if I know it's not stopping in round 2, I can do something a tiny bit better. Yeah.
You could beat 1/2 by a little bit then.
By, actually, so let's see.
Because you
How-
could just keep adding the middle edge each time. Or, does that make sense? The horizontal-
Right. So off the top of my head, I can't tell you exactly how this would affect this. I could code this up and check for you in a minute.
So if you knew the stopping point, then it's trivial.
If you know the stopping point, it's painfully trivial, right? This is just a max matching problem. Just ignore everything. Actually, you don't even need to compute anything. This is the optimum,
Yeah, exactly.
right?
I mean, yeah, you can like, how do you say, let's say it's a type 100, so you stop at a random one of these 5 and you fill it with useless edges to the 100. So that's how you construct it. I mean, you need to change the instance a little bit.
Oh, if you want to show hardness for this promise problem that you either stop at this point or at that point.
Yeah, just
Sure.
if you surround it, you stop at the random guy and do it.
Right. But for initial question, if you have 2 possible stopping times, then the problem is easy, right? I mean, for this to converge to 1/2, I actually need. So if I want 1/2 plus 1 over k, I need k rounds. So 2 rounds is not going to get me better than 1/2 plus a constant. And actually, one of the positive results known before. Oh, actually, here's another way to see this. So I'd mentioned that there are positive results known for bounded degree graphs. Okay? So if you only care about 2 possible rounds, essentially you only care about the edges of round I and round 100i in your example. So it's a graph of max degree 2, so you can get 1/2 plus something that depends on the max degree, which is a constant. Okay, anyway, it's a crazy sidetrack, but okay. Other questions about this? Okay, so this input plus the LP from the previous slide and the general discussion up until that point allows us to show the following result. There is no 1/2 plus constant competitive algorithm for online matching under edge arrivals. Great. So unless there are any other questions for the remainder of the talk, I'll give you some idea of what went into the vertex arrivals result. Okay, so for vertex arrivals, remember we have nodes showing up together with their edges to their previously arrived neighbors. And we have to decide immediately and irrevocably who do we match to. Okay? So now we're no longer happy with fractional algorithms. We actually want an honest-to-God randomized algorithm. And part of the reason we're not happy with a fractional algorithm is that, well, I guess this is a tip of the iceberg of what the results are, et cetera. Part of the reason we're not happy with a fractional algorithm is that such a result is already known. Okay, so in 2015, Wang and Wang gave a 0.526 competitive online fractional matching algorithm for vertex arrivals. Okay, so this is Sam Wang on the right, and Yang Wang is on the left, presumably the older gentleman. Okay, so the natural question here, no one like that joke? Okay. So the natural question now is, can we round this in an online setting? Okay, that's a question. So what I'd like to do is, if I have a fractional matching algorithm, which outputs a matching of fractional value k, so sum of all the edges xe is equal to k, I'd like a randomized algorithm whose expected matching size is k. Okay, so unfortunately, this is not going to work even in an offline setting, because the integrality gap of the fractional matching polytope is 3/2. Or in English, there exist fractional matchings on a graph that might be 3/2 larger than the maximum matching. So for example, if you look at this triangle here, if you assign values of 1/2 to all its edges, this is a feasible fractional matching, right? Every node has sum of values assigned to its edges at most 1. But the max matching on a triangle is at most 1. You cannot take 2 edges on a triangle. They'll share an endpoint. Okay, so if we want a general rounding routine, well, we'll have to lose a 2/3 factor compared to the fractional algorithm. And 2/3 times 0.526, well, that's way below 1/2. So that's too bad. You know what? Forget general graphs. Let's do bipartite 2-sided arrivals. Okay? We know that bipartite graphs were already hard for edge arrivals. Let's do bipartite graphs with interleaved arrivals. Can we round this without losing anything in an online setting? And unfortunately, even here, there's pretty bad news. So in joint work with Ilan Cohen and Soda 18 last year, we showed that there exists no lossless online rounding algorithm, even in bipartite graphs with one-sided vertex arrivals. So in the classic KVV model. Okay, so this is really distressing, right? We have actually, and if you're curious as to kind of what you'd have to lose in general, so here we had to lose a 2/3 term, here you'd have to lose a 7/8, and even 7/8 times 0.526 is below 1/2. Okay, Pravesh.
But the 0.526 thing doesn't improve if you know the graph is bipartite?
No. If it's bipartite with interleaved arrivals, even then this result is only 0.526. Good question, but yeah, no. Oh, that would have been sweet, but yeah. Good, so you know what we're going to do? So basically what this says is if you want to have an algorithm which receives some oracle access to a fractional matching in an online setting and rounds it without losing anything, so every edge E will be matched with probability exactly XE, well, you're out of luck because that's not going to happen. Let's try and forget the fact that we know this for a minute and try and do it nonetheless and kind of figure out where we have problems along the way and maybe see if we can patch it up somehow and get a potentially good algorithm. Okay, so here's one way of trying to match each edge with probability exactly, each edge E with probability exactly XE. So when a vertex V arrives, we run the next step of our deterministic fractional algorithm, get some X values for all the edges, and we'll pick at most one neighbor U of V with probability proportional to XUV. In particular, we'll take as probability XUV over the probability that the algorithm has not yet matched this node U. Okay, imagine for a minute that we have these probabilities. I'm not worried about computation at all right now. Okay, so the same shtick we said earlier about going from randomized to fractional, you can do here as well. Okay, so now we have maybe one neighbor, and well, what are you going to do? Well, if this neighbor is free, we'll actually match to it. Okay, so notice that in step one, we didn't at all inspect the node to see whether or not it's free. So the probability that we actually pick up U in round one is independent of this node U being free. So with probability U free, U is free. This is not a great name, which cancels out with the denominator of the probability of picking U. So we'll actually match the edge XUV, the edge UV with probability exactly XUV. Right? So perfect lossless rounding algorithm. Terrific. We have a 0.526 competitive randomized algorithm. Isaac, why am I lying?
Because your probability is over 1.
Because my probabilities could be over 1, right? I'm picking at most one node U. Each node U I pick with probability PU. Well, then the sum of these PUs better be a sub-distribution, right? Better sum up to at most 1. Otherwise, how am I going to pick at most one guy in expectation? Good. So some of these PUs can be greater than 1. So this doesn't work, which is, I guess, not surprising given what we saw in the previous slide. We cannot round without losing anything. So let's try and do the following kind of simple fix. If the sum of these PUs is greater than 1, I'll just normalize by them. Right? So I'll pick every node U with probability P prime U, which is PU over some of these PUs. So some of these normalized probabilities is exactly 1 in this case. So I can definitely pick one node U with probability PU over some PUs. Okay, so we started maybe with a 0.526 competitive algorithm. If the sum of these PUs, when the sum of these PUs is greater than 1, it's only greater by a tiny bit, then we've lost a tiny bit. We don't match each edge XE with probability XE, but XE over the maximum these sum of PUs can be, and we're still above 1/2 competitive, and we're happy. Okay, unfortunately that's not the case, and actually normalizing this way will lose us too much along the way. Okay, for all fractional matching algorithms that beat 1/2 that we know, if you round this way, you'll get something less than 1/2. Suggestions? So we're matching each edge with probability roughly XE, but normalized by something, so we're losing a little bit. So we'd like to match each edge a tiny bit more. So here's the thing. So notice that in step 1, we're picking neighbors without checking whether or not they're free, and then in step 2, we actually checked if they're free. And if they're matched, we said, well, too bad. This one node I picked is matched. Who cares? I have other neighbors, right? So here's the natural approach then. If you picked an already matched neighbor, run these two steps one more time. Okay, so now every edge has a probability xe over some of these PUs to be matched on the first time we pick something, and some probability of being picked the second time around. Does anybody see what the issue might be here?
You might get unlucky twice.
Sorry? You might get unlucky twice. And just to kind of quantify this, or kind of see when this might happen, if the neighbors of V are positively correlated, so the events that they were matched before is somehow positively correlated, then I might not gain anything from the second step. So let me make this a little more concrete and a little clearer. Imagine all the neighbors of V were perfectly positively correlated. So if I tell you that U5 is matched, they're all matched. If I tell you U4 is matched, they're all matched. Well, if the first time around I picked something and it's matched, what the hell is going to happen the second time? I'm not going to get anything. Right? So the probability of edge E being matched will be xe over sum of the PUs for the first match. And for the second match, it's going to be 0. So overall, I'm still getting xe over some of these PUs. Okay, does this make sense? Danny seems doubtful. I don't know. We're almost done. So if like
50 minutes is a little, sometimes you run out of steam.
Out of pizza.
A lot of pizza, maybe that's a bit fatiguing. So all I'm saying is there's two events where you can actually increase the marginal probability of E being matched from the trivial 0, right? I could match it as the first pick, or I could match it as the second pick. But for me to be able to pick U as V's match the second time around, it has to be that when I tried the first time and failed, U is somewhat likely to still be around, right? Conditioning on the fact that somebody else is matched, somebody else in V's neighborhood is matched, shouldn't mean that U is definitely also matched. Okay? So without getting into details and alluding again to the tip of the iceberg picture from earlier, what we show over too many pages of the paper is that for some version of the algorithm of Wang and Wang, we can actually bound these positive correlations. So we'll lose something from rounding, and we'll actually gain more than enough to still get us above 1/2 by taking the second pick. Yes, CJ.
Is there like a good, convincing reason why you're doing this process exactly 2 times and not?
Oh, yes. So the reason why we do this exactly 2 times is 2 times is enough to beat 1/2. And actually, if you wanted to do it more times, then you'd have to start looking at higher moments, higher correlations. So here we kind of only care about pairwise correlation. I want to know that if I picked you and you were matched, then I still have some chance of picking Isaac afterwards. But if I start doing like 3 choices or 4 choices or 5 choices, I have to look at 3-wise, 4-wise, 5-wise correlations. It's just a pain, and we don't get anything useful out of it. Isaac.
And more generally, if you kept going until you matched somebody, then you'd be a greedy algorithm and would definitely fail.
Fantastic. Okay, another better answer than what I just said right now is if you just kept on going, at some point you'll pick someone, and that's just a greedy algorithm.
But
You could stop after some time or something.
The
Yeah.
number of times you iterate this process has something to do with the probability that
So I'm kind of skipping one kind of important detail. You want to make sure you don't match any edge with too high a probability. Otherwise, it's kind of hard to bound these PU terms. And the more you go, it just starts getting hairy and hairy.
there's no a priori there's no reason you couldn't flip another coin to determine whether you're going to do this
Sure.
process again.
I'd be happy to talk. I feel like with you I can talk about this in more detail, so maybe let's talk about this after. Okay, other questions? Okay, so putting all of this and some and then some, we get the following result. There exists a 1/2 plus constant competitive algorithm for online matching under general vertex arrivals. Good, so to summarize, we show the following dichotomy for online matching under more general arrivals. For edge arrivals, greedy is the best you can do. 1/2 plus a constant is impossible. On the other hand, for vertex arrivals, 1/2 plus a constant is possible, and there's okay, I wouldn't say a nice randomized algorithm, but there is a randomized algorithm that beats 1/2. Before I kind of point out some questions that I feel like are natural, anybody want to pose some natural open questions? Isaac.
Is your second algorithm polytime implementable?
Yes, the second time, the algorithm is actually polytime implementable.
Okay.
Yeah.
Like figuring out the probability the algorithm has assigned already. is
Right.
doable.
Yeah. So basically, like a Monte Carlo thing will give you the same thing up to some error term. And, yeah.
Is there a reason to believe that the LP you have cannot be rounded optimally?
There's no good reason, and I've been trying to build a theory of what can and what cannot be rounded without losing anything, or like characterizing how much you have to lose based on what your fractional algorithm looks like. So far, I don't have a good characterization.
Is there any example of a similar problem where one could prove that you cannot match the approximation ratio of the LP?
Sure. So for online matching, this is kind of what I was mentioning earlier. For online matching in bipartite graphs, think of regular graphs. Okay. If the graph is d-regular, every node has exactly d neighbors. Assigning 1 over d to all the edges will give you a one competitive fractional solution. But randomized algorithms cannot do better than 1 minus roughly 1 over root d. And we actually also know how to match that from a previous paper.
So maybe given that.
So basically there might actually be a separation between randomized and fractional algorithms. So for example, our hardness result shows that no fractional algorithm does better than 1/2 plus 1 over n. There's nothing to rule out that no randomized algorithm does no better than 1/2 plus 1 over exponential in n. Okay, let me point out a few other questions. One of which I think maybe could have popped out a little more easily. The first question is, what's the optimal competitive ratio? Okay. So in particular, for vertex arrivals, we showed that you can beat 1/2. You can get 1/2 plus a constant. The constant is, let's say, not huge. We did nothing at all to try and optimize this, but I think the only number I'm comfortable saying just off the top of my head is maybe 1/2 plus 1 over a billion. So, potentially not the optimal solution. And maybe a somewhat unusual question to end a theory talk with. The original problem studied by KVV, by Kavvaziani and Vazirani, was this very nice theoretical problem. But over the years, we found that this has some extensions of this problem has some really nice real-world applications. And kind of be interested in seeing whether or not there are nice extensions or applications of these more general online arrival models. And I think that's all I got. Thanks. Other questions? Maybe I should have solicited them earlier. Pravesh, yes.
So one final question.
Yeah.
Is it known, so maybe you answered this already, but the LP thingy that you wrote for vertex arrivals, is 0.526 the integrality gap of that LP? Like, is it the best possible thing we could obtain there?
So the LP itself is still the same fractional matching LP. The integrality gap for that LP is 3/2 in general graphs, and in bipartite graphs it's 1. There is no gap. In some sense, the online nature of the problem says that integrality gap is not the problem. So I guess what I was saying earlier about regular graphs, maybe I should emphasize this. The integrality gap of the fractional matching polytope is nothing. It's 1. Okay, 1 is now nothing. Okay. Nonetheless, just kind of, it's not even correlation.
It's not the fractional matching polytope because you have constraints for each
vertex. No, that's a fractional matching polytope. There's the matching polytope, which is you also have these odd cycle constraints. But when we're talking about the fractional matching polytope,
but you have all these subgraphs, right? So it's actually tighter relaxation.
It's a tighter relaxation. Oh, you're talking about the hardness. You're talking about the hardness result or about the positive result?
So so you use this 0.526 approximation result and then give a rounding.
Yeah.
I'm asking, can the 0.526 itself be improved?
As in, can you do better than 0.526 in online settings? I do not know. The only thing I know is that you cannot do better than 0.593. So even there's some gap. You seem confused, so possibly not quite the question you were looking for an answer to. So let's try again.
No, maybe you answered it, but one final time. There are two things going on.
Yeah.
One is the deterministic fractional
algorithm,
and there is an LP for that.
Yeah.
And the LP achieves 0.526 over this bigger class of algorithms, right? And then you say, okay, look, I want to have a simpler algorithm, like randomized thing. So I round it. I have to online round it. So I'm asking, there are 2 steps where you could lose things. Lost something in the second step, rounding step. I'm trying to understand is it possible
to do better in the fractional step? Yeah. So what I was saying is it's not clear whether or not you can do better than 0.526 for deterministic fractional algorithms in online vertex arrival model.
But I guess your result also means you can't do better than 0.593. And I guess that's
No, this 0.593 was known before, but yes. So this.
also imply for this deterministic fractional you can't do better than 0.593, right?
Yeah.
And that separates it from 2/3, which is the 3/2 gaps.
Yeah. Isaac.
So when you discuss this, intuitively, why are you getting just above a half? Like when you start with 0.526 and then you're trying to not round it too badly, where does the half come into it?
Right. So in a little more detail, Wang and Wang didn't actually give one algorithm. They gave a family of algorithms and then spent a non-negligible part of their paper optimizing parameters in a methodic way and not just parameter hacking. And basically we picked one of these algorithms. So if you think of, let me maybe go back to this thing. So remember our first step, we said, let's round by the sum of these PUs, which I'll basically have be XUV over 1 minus sum of the previous X's. For the Wang and Wang algorithm, the 0.526 algorithm, the sum of the PUs will be huge in this case. Okay, so that's a non-starter. So instead we take 1/2 plus epsilon algorithm of Wang and Wang, show that we don't lose too much here, so we'll say we're like at 1/2 minus some function of epsilon, and then we show that we can still get enough in this step to get 1/2 plus some other function of epsilon. All right, so I think I'll thank you for your time, and see you again next week.